Hi, our project today is petroleum upgrading, catalytic refining, and reforming. Our group is Avery Everett, Yanish Walters, Yi Zhang, Nurul Izyan, Binti, Fadel Hamdan, Nur Azwan Zeki. Petroleum is something that contains hydrocarbons, NSL materials, metals, bitumen, and it's obviously location specific. It has been accumulating for a long time, billions of years, and there's many ways to extract it, but we're not here to talk about that today. First, we want to talk about the fractional distillation. It is the first step distillation. We need further refining, and then the refining also depends on our needs. One thing we do know is that we do not want to exceed 360 degrees Celsius while we are distilling, because then that process would be considered a cracking process.
Crude oil is a thick, dark brown liquid found deep in the Earth's crust. It's a mixture of different hydrocarbons, molecules made of hydrogen and carbon. Some molecules in the mixture are very small, just a few atoms joined together. Others are far more complex, with many atoms forming long-chain molecules. But as a mixture, it's useless. The different hydrocarbons need separating. The technique used is distillation. This simple apparatus is set up in a fume cupboard. Mineral wool stops the mixture spitting when it's heated. Crude oil is dropped into the bottom of the tube. A collecting bottle is put in place, and a thermometer level with the sidearm monitors temperature. The final step is to gently heat the mixture by immersing the tube in a hot water bath. The hydrocarbons with lower boiling points begin to vaporise immediately. They're flammable, so it's safer not to heat with a naked flame. As the vapour rises, it enters the sidearm, where it cools and condenses. This happens at about 40 Celsius. The hydrocarbons which boil at this temperature drip down the sidearm and form our first fraction. It's a colourless liquid. The temperature stays at around 40 until all the hydrocarbons with this boiling point have vaporised. The hydrocarbons left behind aren't hot enough to vaporise. Their boiling points must be higher. Once the first fraction has been collected, it's safe to start heating with a Bunsen. As the temperature rises, other hydrocarbons begin to boil. A new fraction is collected at about 60 Celsius. It's slightly yellow in colour. And so the process continues. By carefully heating the oil and collecting the liquids which condense at a number of different temperatures, the many different hydrocarbons in crude oil can be separated. This is known as fractional distillation. On a larger scale, a fractionating column is used. The oil is heated with an electric heater for safety. The vapour is condensed by a Liebig condenser and is collected in a conical flask. Hot vapour rises up the fractionating column. It's a long way to go, and the further from the heat source, the cooler it gets. Most of the vapour condenses on the glass spiral inside the column and drips back into the mixture. Only the hydrocarbons, which are still vapours at the very top of the column, enter the sidearm and condense to liquid. Industry uses the same process, but on a mammoth scale, in huge fractional distillation columns. The hot oil enters near the bottom at a temperature of 330 degrees Celsius. The column becomes cooler towards the top. Fractions which remain as vapour at 85 degrees Celsius go straight to the top and are piped away. Different hydrocarbons condense at different temperatures, running off at various levels. Those with lower boiling points are collected at the top. Those with higher boiling points run off nearer the bottom. The longer the molecules, the higher the boiling point. Industrial distillation separates crude oil into useful fractions, each containing molecules of a similar size.
Catalysts, what do? We need these catalysts because we need them for cracking, reforming, and these reactions will not occur spontaneously, and so we need these catalysts to help us activate the reactions needed to get what we want from the petroleum.
So catalysts, they lower the activation energy, and instead of increasing the temperature, which would cause cracking, the chemistry of the functional groups affect the chemistry. So throughout the structure, we can have several different functional groups such as alcohols, ketones, and aldehydes. However, the more complex, the more difficult it would become to dissociate, which is where resonance plays a role. Alkanes, also commonly known as paraffins, can come in branched or straight forms. In terms of catalysts, these are the simplest to dissociate. The catalysts that are most commonly used are silica alumina at 400 to 500 degrees Celsius in the refining process. They are used by adding high boiling kerosene cut with C11 to C14 isomers, and are then broken into smaller molecules, which then produce C3 to C5 molecules, which are then recombined in catalytic recombination with C7 to C10 molecules, which require another catalyst, which is then another form of cost, which then makes aromatics. Cycloalkanes, CH2N, are less flexible due to their stereochemistry than alkanes, due to their double bonds. As a result, they tend to need higher temperatures and are more difficult to break. More difficult still are aromatics. They tend to have six-membered rings, such as benzene, and do not undergo electrophile addition, which is shown on the slide. In most of the reactions, in terms of catalysts, we have to be careful because of sulfur, which can cause the catalyst to break down and decrease their activation energy, which can cause the catalyst to no longer work, which then requires more energy, more money, and then causes us to then, it essentially breaks down the whole system. Instead, a better catalyst would be aluminum chloride, which can be seen in the Friedel-Crafts alkylation and alkylation reactions. The limitations, however, are alkyl halides that can only be used in these types of reactions, but they don't work on the rings that are already substituted with NO2, C triple bonded with nitrogen, SO3N or COR groups. How does this work with refining? Well, refining is dependent upon the purpose that you're looking for, as shown in the diagram on this slide. So basically, whatever your purpose is, your end goal, your cost is going to be dependent upon that. As you add into the initial distillation, you're going to develop naphtha, kerosene, and gas oil. From there, you're going to end up having to add additional catalysts to do additional refining. And from there, you're going to have to add additional catalysts from there, which adds more cost. Then there's additional RFCC, which is refluidized FCCs, which then you have to take into account the feedstock. So then with these, you have the feedstock, which is gas oil at 316 to 566 degrees Celsius. And from there, you have to deal with NSOs, such as mentioned before, the sulfur, which deactivates the catalyst. On these next slides, we also talk about the primary reactions in catalytic cracking, which we've covered in class, but we just wanted to mention that the beta bond scission and the proton shifting are primary steps. And then from there, we have to take into account that when you select the catalyst, the primary ones that are used are platinum and alumina systems. However, platinum is very expensive, so we tend to use zeolite, which is less expensive. However, its activation is lower, so then it requires a much higher energy, much higher temperature to activate. And then from there, you have to use catalytic reforming to increase the octane number in gasoline. Fast forward a few slides and we see that inside each barrel of crude, you have middle, light, and heavy distillates, which come from the heavy, light, and sour, and medium crudes from different sources, as mentioned before. Essentially, you have to take from your end goal, and your end goal is going to dictate which catalyst you have to choose from. We have to crack our aromatics in order to produce higher octane gasoline, and then to change the naphthenes into aromatics. They all require additional catalysts for their reactions and conditions, and metal catalysts and acid catalysts are going to dictate whether or not the reactions are going to occur and how they're going to occur.
Okay, so to discuss the upgrading petroleum process via catalyst, just a quick introduction. Basically what it's doing for the industry itself is it's helping some fields, or more commonly known like areas that haven't been profitable in the past, that can now be profitable due to new enhanced oil recovery. So this allows for recovery of high viscosity, high density, heavy crude oil after all the breaking down of all the native compounds. The process behind this is known as in situ catalysts to upgrade heavy crude to lighter products. Okay, so an overview of the upgrading itself. Downhill catalysts will act as a replacement to original catalytic crackers used in the conventional oil refining processes. The crude oil itself is reacted with hydrogen gas on the surface of the catalyst, just like in traditional upgrading with catalytic cracking. The differences come in with downhole upgrading because it must also handle all impurities that result in high steam partial pressures, low hydrogen partial pressures, and naturally occurring downhole brine. Although downhole upgrading has been proven to be successful, consistent replication of a startup has been proven to be difficult and is currently only seen in limited commercial applications. So on to the process itself. You first inject catalyst into the wellbore. This can be done by gravel packing method, which is well known, or by a new proponent injection method. The gravel method is well known, but now using almost the same technology, it is possible to substitute gravel for the desired catalyst, which would, in this case, that's what we would be doing. The injection is a step in hydraulic fracturing, which a material like sand is injected into the formation itself
not only into the wellbore. This leads to a better opening of the fracture. Here we see the catalyst being replaced for the sand. Then we must raise the temperature of the area around the wellbore to induce the reaction. This can be done by placement of electrical heating elements or a cyclic injection of steam into the formation itself. Then once the formation begins to increase in temperature, it is common that the well is shut in, so this allows for the breakdown of the heavy crude. So some advantages and disadvantages of using the catalyst is the practical application currently is limited, but in El Canalio oil field in Argentina, using specific catalysts, the oils API rose from 15 degrees Celsius to 24 degrees Celsius. It also had a viscosity reduction from 40 degrees Celsius. This simply means that the oil becomes less dense, which allows the process downstream to be easier and allowed for easier induced flow in the lighter hydrocarbons. Downhole catalysts are expensive, meaning that companies need capital, manpower, and or research capability to do this, which basically most universities are the ones that are researching and implementing these catalysts right now, instead of having, let's say, a large company like BP investing into it until they know it's profitable for themselves. This can be risky because it's still up and coming technology, and not all reservoir conditions are favorable, so it can only be used in certain fields. So just the conclusion of processing itself, although the process is similar to the process used for oil sands, more research needs to be done for the improvement of recovery of high viscosity, high density crude by the way of catalyst technology. Research will be completed primarily, as I said before, by universities until the oil industry makes enhanced oil retraction a bigger priority. The process is shown to be successful in specific parts of the industry with the correct reservoir and implementation.
Now we would like to talk about the comparison with natural gas. First, I would like to introduce the natural gas. Natural gas is a naturally occurring gas mixture. This gas can be found deep inside the earth as a form of solid and liquid hydrocarbons bed. Natural gas needs to be processed before it can be used. There are several compositions in this natural gas, and the highest one is the methane, which is around 87 to 97%, followed by ethane, which is around 1.5 to 9%, followed by propane, nitrogen, carbon dioxide, and etc. The applications of natural gas is to generate electricity and heat, and also used in vehicles, and this is called CNG, which stands for compressed natural gas. There were 3 studies that conducted by several universities to find the best catalyst for the 3 routes of a methane conversion. And these studies are syngas production, steam reforming of natural gas, and also oxidative coupling of methane. For the syngas production, they want to find a catalyst that can lower the production of the hydrogen and carbon dioxide ratio in syngas production. And these studies are conducted at University at Limerick. There were 2 steps of they're doing 2 steps in these studies. First, the activity and stability of platinum on different oxides were observed. The oxides they were using were zirconium dioxide, titanium dioxide, and also aluminum dioxide. Other oxides such as magnesium oxide and silicon dioxide were not used because these oxides do not give active materials. And the next step is to find which metal was the most suitable for the active phase. Only the noble metals such as iridium, rhodium, ruthenium, palladium, and platinum were examined in this step. Here you can see the graph of the results, which is a methane conversion versus the time, and this is in series of temperature. As you can see, at a lower temperature, there were not much difference between the 3 catalysts. At a higher temperature, it shows that the platinum zirconium dioxide is at the most active and stable sample. The platinum titanium dioxide and platinum aluminum dioxide sample deactivated. This is due to carbon deposition, which means a large amount of carbon detected on the material after being used. Now you can see the graph of methane conversion as a function of GHSV at 800 degrees Celsius using different catalysts. As you can see from the graph, there are two metals that were the most active catalysts and the most stable, which is platinum zirconium dioxide and also rhodium zirconium dioxide. And platinum zirconium dioxide should be used since the rhodium is likely to be too expensive catalyst.
Alright, I'll talk about the steam reforming of natural gas. Large quantities of hydrogen gas are required in the petrochemical industry. This hydrogen is used to change the chemical structure of crude oil. Crude oil is a mixture of many different molecules. Some are very light and will have low boiling points. Others are very large and have much larger boiling points. The mixture can be separated by distillation. However, if you do so, you will get a lot of rather useless heavy tar, or not nearly as much of the light hydrocarbon fuel as you want. Most hydrogen produced today in the United States is made via steam methane reforming, a major production process in which high temperature steam, which is from 700 degrees to 1100 degrees, is used to produce hydrogen from a methane source, such as natural gas. In steam methane reforming, methane reacts with steam under 3 to 25 bar pressure in the presence of catalyst to produce hydrogen, carbon monoxide, and a relatively small amount of carbon dioxide. Steam reforming is endothermic, that is, heat must be supplied to the process for the reaction to proceed. For the catalytic oxidative coupling as of the methane to high hydrocarbons has attracted widespread attention as a potential route to ethylene or liquid fuels. Besides research work in catalyst development, a lot of investigations dealt with reacting engineering aspects in order to make this process technically feasible. The objective of the paper is to evaluate the current status in this field. Various aspects as reaction kinetics, reactor selection are different modes of reactor operation and analysis, with the aim to identify reaction engineering means which can be used to maximum the carbon selectivity and yield. Available kinetic models for reaction engineering applications and arrive at the importance of various reaction steps. Also, pre- and post-catalytic reactions is analysis. Since OCM is a complex reaction network of parallel and consecutive, as well as the homogeneous reaction steps, the activity of hydrocarbons strongly depends on the reaction conditions. It is the effect of temperature, particle pressure of methane and oxygen, and total pressure is discussed. Central issue in development of the OCM process is the choice of the type of reactor, possible design of fixed bed and fluid-side bed reactors, the status in their modeling of OCM, best carbon yield achieved in lab-scale unit, as well as novel reactor designs are reviewed.
Next, I will talk about the general economy of the catalyst. As for today, process catalysts play a vital role in the economy. About 90% of chemical manufacturing processes and more than 20% of all industrial products implement catalytic steps in their process. As for example, petroleum refining, which by far has the largest share of industrial products consists of almost entirely of catalytic process. As we can see, this two pie chart shows the world catalyst consumption of petroleum refining and also the chemical processing catalyst on a value basis. Catalyst consumption in terms of petroleum refining has a different pattern which varies according to the refinery configuration in each region of the world. It is expected that the growth rate will be higher in the next 5 years due to the new refining capacity in China, other Asia, and also in the Middle East. Similar to chemical processing, the growth rate will be contributed by the increasingly new capacities such as in the Middle East and Asia. In addition to that, utilization of shale gas will also cause an increase in petrochemical capacity in North America. It is expected that the strongest growth in demand will be through 2021, which is rising in incomes will drive demand for more motor vehicle and transportation fuel, and hence will result in the fast-growing industrial chemical production, particularly in petrochemicals. This growth will somehow be reflected in increased demand for a number of catalysts which will be used in the refinery segment, such as for the catalytic cracking and hydroprocessing. The largest refinery catalyst segment in terms of value are in the hydrotreating and also in catalytic cracking, while the largest volume product are alkylation catalysts. So research has been done to evaluate and analyze the economics of some fuel oil upgrading processes which with and without catalysts. So 7 upgrading schemes as shown were identified as a high distillate production scheme and has been proposed and were evaluated. As we can see, out of the 7 schemes, 3 of them, which are the schemes 1, 4 and 7, were the scheme that has at least one catalytic process in it. Economic parameters such as internal rate of return, payback period and net present value has been calculated for each option. All study schemes were proved to be profitable, and the parameter investigated are sales price, the production rate, feed cost, utilities cost, direct and indirect costs, tax percent and discount rate. So as we can see in table 1, it shows that only scheme 147 has actually produced propylene, which by year 2012 is the most expensive petroleum product, and in addition to that, only scheme 7 has produced the base oil, which is also one of the petroleum products with higher price. So as mentioned before, all these proposed schemes were profitable. However, if we look closer, based on table 2, we can see that out of all schemes, scheme 7 has the highest NPV value, IRR, and payback period, which indicate the most favorable option economically. So as generally, all options doesn't show a very significant difference in terms of NPV. This is because the capital investment were very high for scheme with catalytic processes, even though they produce the most expensive products. Catalyst is a big chemical purchase for all upgrading processes and require high technology, which is turned out to be a very costly.
From our project, you can see that catalytic processing in petroleum fuels definitely leaves room for improvement. However, over the next few years, over 2018 to 2021, we definitely will see growth, as well as some hiccups in the research development field. From scheme 7, we do see that there will definitely be some room for market value. That being said, we do also need to do research on which catalysts will be best, but from all of the research provided, the sources are definitely the areas that we need to look at. platinum catalysts from the natural gas area show that zirconium oxide showed promise, but also it was most expensive. However, it was also favorable and very stable. We also saw that steam reforming of natural gas was used highly and most favorable in oxidation. We saw that the chemistry of catalytic processing was used throughout most of the market, but we also saw that many studies increased the economic rate of return. The downhole catalysts act as replacements for the original catalytic crackers in the refining processes. And then we also saw that proppant was used to inject in hydraulic fracking. Catalysts aren't going to go away, so we need to use them, and we need to learn how to use them well.